Okay, so to lighten things up a bit for this last lecture, just to remind you, next week will be for questions about the assignment. So there will not be lectures, but these hours will be just for questions about the assignment. Okay? So this will be just a brief introduction to deep learning. I'm going to talk a bit about how neural networks evolved and became such an interesting class of models, and deep learning, why the big success in these recent years, advantages and some problems that have been overcome recently. And then I'm going to talk a bit about autoencoders as an example of using deep neural networks. So there are many different applications for deep neural networks, but I'm particularly fond of autoencoders, so I'm going to give this as an example. So let's start first with a bit of history. We saw the origin of neural networks in the 40s with the model, the mathematical model of the neuron. Then in the 50s, Rosenblatt proposed the perceptron, and at the time it seemed like it would be a revolutionary thing capable of learning autonomously and so on, until it turned out, they found out that this was just a linear classifier. So basically the perceptron is the same as logistic regression, just trained in a different way, so it cannot do that much. But so in '69 we had this paper of Minsky and Tappert, which mentioned that the perceptron would not work. We would need to have a connected layers for the networks, and now the problem was how they could be trained. So since there was no way of training networks of perceptrons, of neurons, then there was no way of using this. So this became a bit of a disappointment. So for during these decades, 60s and through the 80s, artificial intelligence in general became a field that was not very, very sexy at the time, because those first approaches with logic and so on became a bit stagnant. They seem to be a bit limited, and also the part of neural networks and so forth also was very limited. So that first hype of having intelligent machines and so forth was really a disappointment at this time. But then something started to appear, like the backpropagation algorithm, and so in '86 they figure out how to use backpropagation to train multi-layer networks. And then at that time, also in the early 90s, machine learning also started to become very much more promising again, because of things like the kernel trick for support vector machines. And now, instead of having just linear classifiers, we could have models that did linear classification, but first implicitly did some nonlinear transformation, so that things became a lot more powerful. Also, multi-layered networks and convolution networks started to be used because of backpropagation, and they started to be used in practice for example, processing bank checks and things like that. Another innovation was the beginning of these benchmark databases for machine learning problems. But even so, at the beginning, there was not much success in deep learning. And in recent years, we have other changes. For example, in 2007, one way of solving the problem of when you have many different layers, we're going to look a bit better at that problem in a few minutes, but when you have many layers, training starts to slow down a lot. So there was this first trick of doing unsupervised pre-training layer by layer, and then stacking them already pre-trained and doing backpropagation only on the full network to adjust the parameters finally. But really the big innovation in techniques was the rectified linear Unix, and I'm going to explain why. And this really gave a boost to the ability to use deep neural networks. And also hardware. So general purpose graphics processing units enabled those matrix multiplications that you need to do repeatedly to train neural networks to be done distributedly in graphics cards. And more recently, we have even specialized processing units, for example, the Tensor processing unit for Google and the Intel Nervana processor for doing neural network computations.
How much more efficient in resolving problems neural networks compared to traditional algorithms?
Mm-hmm. Okay, so I'm going to talk a bit about that. It depends a bit on the data, but the big thing that we can do with deep neural networks is that instead of having this step of feature extraction where someone must figure out which features to use, for example, with support vector machine, then you feed them into the support vector machine which does the nonlinear transformation and you get the results. With deep models, you basically stack a series of nonlinear transformations, and the model itself will start to learn which features are more useful for the final step. So basically, you can, instead of trying to manually extract features from images, for example, the convolution network, the different layers, will start to specialize on different kinds of features that appear on the image, and so this automates the feature extraction process. This is one of the big advantages of deep learning. So this is done, we saw this on the exclusive OR problem, where we can do these nonlinear transformations to get a new representation of the data. So basically here you can see the exclusive OR. If you have 0, 0, it gives 0, 0, 1 or 1, 0, it's 1, and 1, 1 is 0. And the network, the hidden layer, is doing this kind of transformation. Not exactly the same, but it's making it so that it's easy for the final layer to get the results right. So you can do this with 2 layers or 3 layers and so on. And when you stack layers, you get different transformations. For example, this could be the input space. You have 2 classes like this. The first hidden layer does one transformation, but it's not quite ideal for separating. But then the second hidden layer transforms this further, and the final neuron can easily distinguish between the red and the blue classes because it's looking at those transformed representations. So we can think of these as nonlinear transformations that are automating feature extraction, so that the last layer of the network can easily solve the problem that we wanted to solve. But what made it so that this became more advantageous to use than traditional machine learning algorithms? And basically, aside from the hardware and some software innovations, some technique innovations, one big issue is the size of the data sets that we use. Because deep neural networks have a huge number of parameters, and if you don't have a large data set, then you're just overfitting your data, and it's very hard to make it work. So when you had, for example, in 2006, this image classification problem that people were trying to solve, this Caltech one data set had about 100 categories, but about 50 images per category. So on average from 40 to 800, but the average was about 50. And classical computer vision segmentation and machine learning models worked with about 26% error in classifying these images. The computers were also slower, but the main problem was this. If you have a small set of data, then classical machine learning approaches where we manually extract features and then apply these kinds of algorithms that we've been looking at perform better than deep learning, because deep learning will tend to overfit too much. But then when we get to for example, the ImageNet database, this has 1.2 million images in total, 1,000 categories. Already in 2012 there were rectified linear units and general purpose GPUs and so forth. So that combination, not only were people able to train deep neural networks, but also the data set was much larger. So we reach a stage where the performance of deep neural networks now starts to pass that of the other machine learning algorithms. So basically, from this time on, we have in 2012 50% error on the top 5 classifications with AlexNet, and then 13.8 overfit, VGG, and so forth, until 5.7. So this starts to become equivalent to the error rate of humans. So at some point, you cannot go down much farther because the images themselves have some classification errors because of the human error in classifying them. But we are approaching, in these kinds of problems, the probability of error of humans, and this is all with deep models. So with this kind of data set, the classical approach no longer can be competitive. And this is the kind of models that you have. So this, for example, is the GoogleNet. We have all these different layers. This is basically the architecture of this network. These are convolution layers and then pooling, and then they are split into different pooling sizes and brought back together again. So if you can imagine all the parameter weights that we have in this network, this is many millions, and so you need good hardware and lots of data to train this adequately. So basically, if you have a reasonable small data set, then it's not very useful to train a deep learning model. Although, if you have a small data set of images, you can use pre-trained models in lots of images and then apply to your own. But if you have a very large data set, then these become much more powerful and useful. So this is basically one of the big advantages is if you have a classical approach, you do feature extraction manually. For example, you have text, you gather different words, you count frequencies, you create vectors with the different words and so on. For images, you can do segmentation and colors and different algorithms to detect the orientation of bright patches and things like that. But this is labor intensive, and if you want to solve a problem, you need to dedicate a lot of time to actually figuring out which are the best features to extract. So with deep learning, basically you feed in the raw data and you add stack layers, enough layers, so that eventually the network finds a good representation, extracts the right features in order to solve your problem. And this is not only good for when we have a hard time explicitly finding the right features. For example, when training the network to play Go or StarCraft or to identify images and things like that. But it's also good when we need to adapt to changes in the data itself. So for things like adversarial systems where you are detecting, for example, fraud in commercial transactions, but when you start to detect some particular trick or fraud things that criminals are doing, then the landscape will change because they will stop doing that and will start doing something else. And you need to retrain everything quickly. So if you're doing this manually, it would be a time lag, a considerable time lag. But if you can use deep models, you can quickly retrain and keep up with the changes in the system. So basically, this is done because we have this nonlinear transform. We saw this with support vector machines, but with artificial neural networks, we have different layers where we have nonlinear activation. So if we have nonlinear activations and we stack them, we are continuously transforming things nonlinearly, and we can improve the results that way. So this is an example from convolution networks where the first layer is responding to things like colors or rough bands and orientation on the input and so forth. But then the next layer is now receiving as input the features mapped by this previous layer. So now it can respond to more complex things like circles, curves, and this one already starts to respond to things that look like objects, like a balloon or something like that, because they can gather features from the previous layers and start to become more sophisticated at what they identify in the image. So basically we have automated feature extraction instead of having humans do this. Now, there is also an issue of why we need these many layers. Because in theory, if you have a good enough nonlinear transformation, you could solve any problem in one step. And we can demonstrate this. This is the universal approximation theorem. If you have a neural network with one hidden layer, you can locally approximate any function by just adding enough neurons and adjusting the parameters. So whatever the function is, if you have enough neurons, you can approximate the function. So in theory, with one single hidden layer, it would be all that we would need. However, if you stack nonlinear transformations, you can make greater oscillations, that is, greater changes from small differences in the input. You have large differences in the output with fewer neurons. So actually, although in theory you could do things with one single nonlinear transformation, you would actually need more parameters for that than if you stack nonlinear transformations. So with deep networks, we can get the same kind of the same shattering ability, so the same VC dimension with fewer neurons than if we were using just a single hidden layer. So this is the practical advantage of these deep models, is that they sort of automate the feature extraction process. We just let them do the transformations as necessary, and they are better than just using one huge nonlinear transformation, because we can do that with fewer parameters and with a smaller search space for the optimum there, less overfitting and so on. But one problem that had to be solved to make deep neural networks work is that when we apply backpropagation, so you remember, to train a multi-layered network, we need to propagate the derivative of the error from the end and across the activation function and the weights and so forth, and do this for all the different layers. So a problem here is that if you use a function like this, for example, a sigmoid activation function, for larger values, the derivative tends to 0. So if we go away from the center point, the derivative tends to 0. And if the derivative tends to 0, since we are multiplying our derivatives here, then everything will tend to 0 and our model is not learning. So each update will hardly change the weights, and everything is getting bogged down during learning. So consider, for example, here we have this data set, the blue and the orange points. We have the X and Y as the input. We have 8 neurons in the hidden layer, and we can train this fairly quickly. These were 370 epochs, and it learned to separate this data. If we put a more complicated data set, for example, these spirals, they are harder to separate. One hidden layer seems to not work very well with 8 neurons. Of course, we could arbitrarily increase the number of neurons. That could work, but eventually we start overfitting. So we can add different layers, stack the nonlinear transformations, but now things don't seem to be working. These were nearly 1,500 epochs, and we still don't have any good separation there. We can add more layers, but things seem to start getting worse, so 2,000 epochs and no good results. So this is because of the vanishing gradient. We are stacking layers with this activation function. When we move away from the center of the sigmoids, the derivatives tend to 0 and learning stops effectively. So this was one big innovation, the rectified linear unit, that solved the problems that were appearing with the standard activation functions like sigmoid or hyperbolic tangent, these kinds of functions that have this S-curve and saturate at the extremes. The rectified linear unit is a very simple function that has output 0 if x is below some threshold, or below 0 if you use a bias value, and output x if it's above that threshold. So when the neuron is active, the derivative is always 1, because the function is merely the epsilon is equal to x, so the derivative is always 1, and it does not saturate. There is the problem that the neuron may die, because if you go too far down here, it will never leave 0, so it will never do anything. But if it's active, then it still learns. There are some modifications of ReLUs that use a slight slope here or some leakage, but the main idea is that this elbow here is enough to give a nonlinear transformation. So you cannot just have a linear output. If you had just the x here, then when you combine different layers, it will just be a single linear transformation. But this elbow here that you can adjust with the bias value is enough to give this nonlinearity. And this becomes much faster because now the derivative does not disappear. So this is the problem, trying to solve this problem with the sigmoid activation. After nearly 1500 epochs, we still don't have any results. With rectified linear units at less than 300 epochs, we already can separate the two classes very well, because the derivatives don't disappear, so the whole thing learns very fast, and we can add more layers and it doesn't stop working because we solve that vanishing gradient problem. So this is basically why we have such a success now for deep learning. First, if it works, it's very good because you don't need to do a lot of manual work and try to figure out the features and so on. You just dump the data in and let the layers eventually find the good representation. Also, it needs a lot of data. But nowadays there are many problems where we have a lot of data. And finally, you need good computers and also these tricks of rectified linear units and optimization algorithms and so on. There are lots of things I'm not talking about, but some techniques that have been developed in the last few years that make all the difference. So now we can train these models if we have enough data and things work well. So let's see an example that I chose, autoencoders, because they are different from most of the things we've been seeing so far, so they fall closer to that manifold learning we saw briefly in one class, but they are different from clustering and classification. And also because I like them a lot, they seem to be a lot more closer to how we humans learn things. So the idea is that we have a network that receives an input and then outputs the same thing as the input. So this is why it's called the autoencoder. It's outputting the same thing that you are giving it in the input. So we call this first part the encoder that converts internally the input in some kind of representation, and then the decoder does the opposite and gives us back what we put into the network. Now the question is, why do we want to learn to train a neural network to give us what we already have? So this is the thing that may not seem very useful, but it can become useful if we force it to do some trick there inside. So in a sense, this is unsupervised learning because we are not labeling our data, but from the perspective of the network, it works exactly like supervised learning, because since we know that the output must be the same as the input, we can measure the errors, backpropagate the errors. So the network is learning with backpropagation as if it was supervised learning. But from our perspective, we can just dump a lot of images or data, whatever we want. We don't need to label anything, and it starts working. But now what interesting things can this do? The idea is that this part here will have some useful properties because of the way it's representing the data. So the trick with autoencoders is to force them to do something useful. One way of doing this is to try to, for example, reduce the size of the representation. So this would be an undercomplete autoencoder where the size of the encoded part, the center of the autoencoder, is smaller than the input and the output. For example, this is a classical example, Mitchell's autoencoder, where we have 8 inputs and 8 outputs. We are training the network to output the same as the input. Each input is 0 except for one that is set to 1. So it can be the first one, the second one, and so on. So these are the possible combinations of the inputs. We train the network to output the same thing, but then in the middle we only have 3 neurons. So here the network starts to learn different combinations of binary representations of 8. They are not necessarily in order, but we have the 8 different combinations of the innermost neurons that encode this part that represent the 8 different possible inputs and outputs. So this is an example of an autoencoder where we can get we can learn the manifolds, for example, structure of the data by compressing the data into fewer values, into smaller vectors. Another thing that we can do is we can use an overcomplete autoencoder, or one that has the same number of values here, but we use regularization to try to force it to learn something interesting. For example, a contractive autoencoder uses this regularization term that tries to minimize the derivatives of the weights as a function of the example. So basically, it forces the network to not only reduce the size of the parameters, because the smaller the parameters, the smaller the derivatives will be too, the gradient will be, but also to try to find the places in the target function, in this loss function, so the error between the outputs and the desired outputs, regions of that function where the derivative is closer to zero, or where things are flatter. And this contractive autoencoder will train the network to be less sensitive to small perturbations in the input and find the most important aspects or relations in the data. So this representation looks at those derivatives of the network for particular examples and represents the singular value. So this is a singular value decomposition of a very large matrix of values, because the activation values of the network are many. They are all the neurons there. But we can see that for this is the handwritten digits example. We can see that the layers are finding relevant aspects, so the derivatives are higher in particular places of the image where the image has some information. And the same thing for this. This is a horse. I don't know if you can see it, but you can find different places where you have this contrast, where if you compare with what you obtained, for example, from principal component analysis, this does not seem to make any sense. So it's just finding whatever pixels are on or off or somewhere in the image. So by forcing the autoencoder to find solutions with the smallest gradients and also the smallest weights, because that affects the gradient, it forces the autoencoder to find the most relevant attributes in the data. Another thing that we can do is to force fewer activations. This is in sparse autoencoders. We can have some probability of the neurons to be active, and we force the distribution of active neurons to be close to what we would expect with that probability. This uses this Kullback-Leibler divergence. We talked about this, comparing different probability distributions. So suppose you want that in the middle layer, only 10% of the neurons are active at any given time. And so this forces the network to try to approximate that, and it gives things like this. For example, this was the map trained with images of 10 by 10, and then we have these 100 neurons in the inner representation of the autoencoder using a sparse autoencoder. So each neuron is trying to specialize into different aspects of the image, and these images represent what images best activate each particular neuron. So you can see that one neuron is looking at bright spots there in the corner, another one at the flash in the diagonal, another one at the bright spot here. So since we are forcing only a few of them to be active for any given example, they are specializing into different aspects of the example. Another way we can use denoising autoencoders, where the compressed representation is generated by the encoder by adding noise to the input. So we add random values, or we set some random inputs at 0, and then we force it to reconstitute the original image without the noise. So in this way we create an autoencoder that can remove noise, and that finds a compressed representation that ignores noise when it represents things. One particularly interesting type of autoencoder is the variational autoencoder, where the encoder part does not learn actual values that are passed to the decoder, but learns parameters of probability distributions. For example, if we use Gaussians, For each example, the encoder will output a standard deviation and a mean for different Gaussian distributions. And then the decoder receives a random value taken from those distributions. This requires an interesting trick to apply random back propagation here, because here we have a random roll of the dice. So basically what is done is the encoder model is computing, it's trying to learn the mean and standard deviation of the distribution, and this passes on to the part of the decoder, but we also add a random value here. We multiply by the standard deviation and we add the mean, and this is just a normal with a mean of 0 and standard deviation of 1. So we can use back propagation across this gap where there are random numbers, but then by also applying those Kullback-Leibler divergence to make these distributions more independent, what we get is that those inner neurons are learning parameters for aspects of the data that actually make sense. For example, we have one neuron that determines the style of the number and another one that determines what kind of number it is, and we can actually adjust those to generate new numbers. So this was trained with the handwritten digits database, and one of the neurons determines whether the number is thicker or thinner or more slanted or more straight, and the other one determines which number it is, and we can then mix them together. For example, we can write an 8 with a thicker line, or a 3 with a thinner line, or a 1 that is more slanted, like italic or something like that, just by changing those parameters. The same thing with faces. We have the face of the person, and then the style, which has the hairstyle and the eyes and the look, and we can mix them together and put the face of one person with a style that is more similar to another. So this is interesting because of the way the autoencoder captures relevant independent features of the data. Another thing that we can do is to use convolution autoencoders. So convolutions are operations that are applied to a small window of a large input space, for example an image, and we repeat the same operation and produce a map of features. We do that with several different convolution kernels. So we can take the image, we produce several maps of different features, and then we do that again, and then we can do it back and generate the image again. So this means that we can create this inner representation of images where we try to reconstruct the image on the output to be the same as the image in the input. So one thing that this can be used for is deepfakes. So we have Jimmy Fallon here and John Oliver. We train an encoder, an autoencoder, where we put some slightly distorted images of Jimmy Fallon, and we get, maybe I can just switch this off for a bit. Okay, so don't fall asleep now. We have this slightly distorted image of Jimmy Fallon. We pass it through the encoder and we force it to learn to restore the image to the original image. So this is the decoder for Jimmy Fallon and the encoder, and we do the same with John Oliver, with images of John Oliver that we input distorted. We use the same encoder, so this is shared. We are using the same network that's learning with some images of one and the other, but we use a different decoder for John Oliver. So this decoder converts from the encoded space to John Oliver faces, this one to Jimmy Fallon faces, and this one encodes either of them to the same embedded space, to the same manifold there. And then what we can do is we give the image from one, for example Jimmy Fallon, and output and use the decoder for John Oliver. So you can see here, this is a video of Jimmy Fallon doing his routine, and this is the face replaced with John Oliver. And we can do that automatically frame by frame by simply using the same encoder, but then the specific decoder for the person we want to output. There are many applications of this that I cannot show in the classroom, but you can probably find them in Google. But this is one way where autoencoders can learn the structure of the data, and then you can use them to do some things like this. In fact, there was a recent case where some people used autoencoders for sound. This is an example for image, but the idea is the same for sound, to mimic the sound of some guy that was the head of a large company, and they called his lawyer to make a transference to Ukraine of some tens of thousands of dollars. It was urgent, so he did the transfer, and then they lost the money because it seemed like his voice, but it wasn't. So these things are starting to have some practical applications. So to sum up, basically with deep learning we are using the nonlinear transformations, stacking them in order to automate a lot of the process of feature extraction, of finding the relevant features in the data. Now the recent success depends mostly on some techniques, some innovation in techniques, optimizers, activation functions and so on. A lot of progress in hardware, you need good hardware for this, and also the availability of data. So the more data is available, the better deep learning models become. I've shown autoencoders as an example just because they are my favorite, but you can have this for classification, for clustering. Also there are deep models for clustering. You have recurrent networks for modeling time series and sequences of events and so on. So if you want to read a bit more about this, there is a good paper on Nature. It's from 2015, but it's a good one from the grandparents of deep learning, more or less, so the big figures of deep learning, and you can see a survey, an overview of this. Yeah.